So I'm going to present first a few definitions at a high level, maybe not fully motivating them. So first one is this thing called a planar 3 tree. And it's a very simple thing. It's any graph that you can get in the following way. You start with a cycle on 3 vertices. So it's a planar graph, meaning that you can draw its edges without any crossing. So you start with this cycle on 3 vertices like this. And if you draw it without the edges crossing, then there's an inside and there's an outside. And what you do is you place a vertex inside. And you connect that vertex to each of the 3 existing vertices. So you can sort of imagine that as there was the first triangle, the outer one, and then I took another one and attached it to the outer one, like this. Now you pick any of these inside faces, and you do the same thing again. So now there's 3 inner triangles. I pick any of them, put a vertex in it, connect that vertex to the 3 vertices of the triangles it's in, and I repeat this as often as I want and in any of the faces that I want. Okay? So in this picture, that looks something like right, so that was me. First one, that's this vertex attaching here, and then I attached to in here, which looks like me attaching, I think it's to that, and that. And you do this, you know, wherever you want and as much as you want. So over here, that's something like, this was the second one, so something like that, and keep going. Okay. That thing is what's called a planar 3 tree. And why a tree? Well, in many ways, it resembles a tree. So one way to think of trees is, well, the way you can make a tree is you start with a vertex and you attach another vertex to it. And so that gives you a tree with 2 vertices. And now if you want to make a tree with 3 vertices, you take a vertex and you attach to a vertex of the existing tree. Like so. I mean, you can't help but do this if you draw trees, unless you're really strange and you draw separated trees and then connect them in some way, but that's error prone. The most common thing is this incremental way of drawing trees, and the same thing's happening here with these planar 3 trees. So it's just triangles inside triangles. Okay. So a couple of things. Why do we care about these things? Well, as you might imagine, there's they have a lot in common with trees in terms of the sort of graph properties that you have of trees. Now, trees have no cycles. This obviously has lots of cycles. In fact, even the simplest ones have cycles. But one of the properties that we saw of trees is that whenever you give me a tree with, let's say, n vertices, I can always find a vertex that if I remove it, I get disconnected trees, each having at most n over 2 vertices. So trees have these balanced separators of size 1, so 1 vertex. These things also have balanced separators, but they're not of size 1, they're actually of size 3. So you can always find somewhere in there, if you give me even a big one of these things, a nice triangle, maybe like, I don't know, there's no good example here. Actually, here's a good example, like this one, that if I take it away, there's some stuff inside the triangle, there's some stuff outside the triangle, and none of them is more than 2/3 the total number of vertices. So nicely balanced in a way. Makes them really handy for divide and conquer algorithms. When we studied separators, that's what we were looking at in planar graphs. So the planar separator theorem told us we could always find square root n vertices that nicely split our graph into two pieces, which were neither of which was too big. If you go to planar 3 trees, then you can find 3 vertices that do it. So you don't need square root n. It's a very small number. Okay. Good. So that's the first thing I want you to remember is these planar 3 trees. And actually, often when we think of this picture is nice for looking at them. But often when we think about them, this picture is a more useful thing. And the one way to think about this picture is you start with on the second step. So you've got these 4 vertices here. And you imagine, so these are the vertices, let's call them 1, 2, 3, 4. And then when I do add a vertex in here, so like this vertex is being added to the face 1, 2, 4. We'll call this vertex 5. And you think of that as a child of this thing. So 1, 2, 4, 5. Right, there's the 1, 2, 4, 5. And then if I, put something in here, this is face 2, 3, 4, 6. So then I would do 2, 3, 4, and the new vertex 6. And if I put something, let's say, in this face, which is 5, 4, 2, and the new vertex is called 7, then I go here, 5, 4, 2, 7. And actually from this picture here, you can reconstruct this thing. Start there, and then you can either do this one. This tells you this tells you have the picture with the 4 vertices and the 3 faces. And this tells you in the face labeled 1, 2, 4 that you had already, put in the vertex 5. And then from here in the face that is labeled 2, 3, 4, put in the vertex 6. And from here in the face that's labeled 2, 4, 5, put in the vertex 7. So you can deconstruct it that way. And actually, finding the nice triangle that splits this thing into 2 parts of equal size is really just looking for an edge in this tree, which splits it into 2 nice equal sides. Because if I look at an edge in this tree, you'll see that the difference between what's written here and what's written here is just there's one vertex that left from here and one vertex that appeared here.
Sorry, Pat.
Yes?
Would you be able to move the camera a little bit? We can't see the other the side that you're writing on.
I can try. Oh, yeah. So I can't tell if
it's all good now. Yeah.
How's the focus? Is it okay?
Yeah, focus is fine.
Yeah.
I'll try not to unplug anything. Okay. Yeah, so the point is that in this representation here, which is actually called a tree decomposition, if you look at an edge, that corresponds to a triangle in the graph, because the two endpoints of this edge are these nodes that have three things in common. In this case, it's 2, 4, and 5. Okay? All right. So great. You have these things. They're called planar three trees. And, you know, this is just the picture I want you to remember. Keep putting vertices inside of triangles. And this representation here is equivalent. And the useful thing about it is it shows you a nice, this representation is a tree, and it kind of gives you a nice way to understand why you should be able to find three vertices that if you remove them, split the thing into two nice equal sets. That just corresponds to an edge of this tree that has, you know, about the same number of nodes on this side as on this side. All right. That's the first thing. The next thing is triangulations. Triangulations are very different beasts. So they are the edge maximal planar graphs. So meaning that they, it's not possible to add an edge to one of these graphs while maintaining planarity. So this is not a triangulation because I can put in, for instance, this edge and it's still planar. And it's still not a triangulation because I can put another edge in here, like, I don't know, this one, and it's still planar. And now there are no more edges that I can add, or no more new edges that I can add without crossing one of the existing edges. Okay. All right, so we've looked at these before. We know a lot about them. There's a formula that will tell you exactly, if you give me the number of vertices, I'll tell you exactly the number of faces and the number of edges in this thing. That's all good. But they're very different than these planar three trees. So for example, since every planar graph is contained in a triangulation, there are many things that I can say that if they're true for triangulations, they're true for every planar graph. And for example, for these planar three trees, I said they have balanced separators of size 3 with 3 vertices in them. These things do not have balanced separators of size 3 in general. We saw that actually the best results and the best that they're the best result possible is if you want to split this into two parts that are about the same size, you might need root n vertices to do that. Okay. All right. So that's item 2. And then the third item that I want to talk about is breadth first search, which again we've talked about before in this course. And for my purposes, it will be helpful to just stick in an extra vertex which is adjacent to these things. And then say, well, let's look at the breadth first search tree of this, rooted from here. So that just means this is the root of the tree. It has 3 children, which are the 3 vertices on the outer face. And so that's level 1 of the tree. And then level 2 of the tree is any vertex which is adjacent to a vertex at level 1. They should pick one of the vertices at level 1 to which they're adjacent. So for example, that is it for a level, no, this one. And that's it for level 2, and then a level 3. There's not much left, so we could do this, and this. So if I look at the levels, here's one of them. That's the level 1. Here's a level 2. And then level 3 is in here. Okay. So kind of works its way in from the outside. All right. So here is what I would like to prove, which is to give a relationship that describes these triangulations in terms of these planar 3 trees and these breadth first search levels. Okay. And the link, there's a lot of ways to see it, is something that I'll call a tripod. So we're very quickly going to get away from precise, exact pictures like this and move to much more sort of cartoon type pictures. But what a tripod is you think of it the following way: you find 3. You find a triangle in your graph, so a triangular face, that none of its edges show up in the breadth first search tree. So for example, there's a few of them, but let's pick this one. Okay. So you take the 3, starting at those 3 vertices, you take some paths going up in the tree. You decide how far up they go. So for example, there's an example where each of the paths has length 1, but they could have more, they could be longer than that, and they don't all necessarily have to have the same length. Okay. Good. So really abstractly, so if this is imagine the BFS tree, I draw it with the root up here going down. What does a tripod look like? Well, it has 3 vertices. If you think about it for a few moments, you'll realize that those 3 vertices have to be on at most 2 BFS layers. So something like this. And then what do so that's the center of the tripod. These things are the legs. What do the legs look like? Well, they are going up in the BFS tree. So it looks something like. So there's an abstract picture of a tripod. All right. And a few things that I'll to look out for. So these legs can be as long as you want. They're not allowed to join each other, so they should all be disjoint. But they can also be as short as you want, and they can even be empty. So I could decide, for example, that I don't want a leg coming out of this point of the triangle, and I don't even want this vertex of the triangle really to be in the tripod. So for example, I could have a tripod. Well, let's make one. Let's say I'll pick this vertex to make a tripod from. That's allowed, right? There's no edge of this this triangle in the breadth first search tree. And so then here could be one leg. Here could be another leg, which is just the one vertex. And on here, there's no leg at all. Right. So that would look like, you know, over here would look something like this, this, and that's it. Okay. All right. So I'll state the theorem and then we'll tell you what all the words mean. Every triangulation G and every BFS tree T of G has a partition of the vertices of G into, let's call that partition P, into tripods such that G, the quotient of G and P is a partial planar 3 tree. Okay. All right. So triangulation, G, we know what that is. BFS tree, we know what that is. So you give me a triangulation, you give me a BFS tree. And this theorem is telling you that I will be able to find a partition of the vertices of G. So partition, remember, means split the set up into sets that don't overlap, but that completely cover it. So each of the parts of the partition is a tripod, like I've drawn here. So I'll draw a whole bunch of tripods on this thing. They're all disjoint, so no two tripods share a vertex. But together they cover all the vertices of G. And then say that this quotient graph ends up being a planar 3 tree. What is this quotient graph? So in general, and this doesn't really have to do with triangulations. If you give me any graph, and then you give me some of its vertices, there may be edges between those vertices, and edges going out to other vertices. So let's say this set of vertices is, let's call it S. And if I take the quotient graph G, say divided by S, that means the graph where I take all these vertices and just make them into one. So all the edges inside this set, they kind of disappear or they become self-loops. And what you get is a graph where instead of all this mess of vertices, you just have one vertex, you can call it S, and everything that any vertex in S was adjacent to, that new vertex X in the smaller graph is adjacent to those. Okay, so that's what, if you give me one set of vertices, and I do this contraction operation, then that's what happens. The set becomes a single vertex. But here we're not talking about one set of vertices. We're talking about a whole partition of the vertices. So the picture looks more like this. I have G. I have a whole bunch of sets of vertices. All right, so I've partitioned the vertices of G into little sets. There's a bunch of edges. Some of them live inside the sets, and some of the edges go from one set to another. And so this is G. These are the parts of P. Then I do G divided by P, and I get some graph that has one thing for each part. And there's an edge between two things in the contracted graph, if and if only if the corresponding parts have an edge between them. So, for example, there's a green part here and a pink part. That's going to turn into a green vertex and a pink vertex. And there's an edge between those two things in the contracted graph because there was an edge from one vertex in here in the green set into a vertex in the pink set. Okay. All right, so that's the quotient graph. And this theorem says that I'll be able to do that. So find this partition into these crazy things called tripods. So each set in here is a tripod. And then when I contract each of those tripods, so pull in all its legs into the center triangle, then what I get is a planar 3 tree. That really simple kind of graph that looks like this. Okay. All right. So would anybody like to ask me any questions? So the obvious question is why? Why would anyone want to do this? So I'll explain a little bit why you might want to do this. So this graph here, the quotient graph, we call it H. And we've got these BFS layers. Right, so somehow I see that each vertex in H is basically 3 of these legs, I mean, corresponds to a tripod, which is just 3 legs here. So 3 of these BFS layers. So sort of, and I can call these legs like, I won't call them anything, but so what do BFS layers look like? Well, BFS layers, they're just the obvious things. There's a layer 0. There's things in layer 0. In this case, it's just one thing. Then there's things in layer 1, which could be adjacent to things in layer 0. And then there's things in layer 1, which could be adjacent to things in layer 2, and and so on. So things in one layer can only be adjacent to stuff in the layer before or the layer after. And if you think of that in terms of quotient graph, so again, right, so the BFS layers, they're also a partition of the vertices, right? There's part 0 has just this, part 1 has the 3 vertices, part 2 has these vertices, part 3 has these things. Now, if I were to take the quotient from that partition, what do I get? Well, everything in one layer contracts down to one vertex. And if I look in one layer, so that means one vertex in the quotient is a whole BFS layer. And what's it adjacent to? What other vertices in the quotient is it adjacent to? Well, if you're on BFS layer I, you can only be adjacent to things at layer I minus 1 or I plus 1. So if I take G and take the quotient on the partition, which is the BFS layers, then actually what I get is a path. Right? Everybody's only adjacent to the layer above or the layer below. On the other hand, if I do this, this partition that this theorem describes, and I take the quotient, then I get somehow a planar 3 tree. And now I can think of every vertex in my graph is, well, it appears on some BFS layer. So if I look at some vertex of my graph, like this one, it appears on some BFS layer. That is, in this case, 0, 1, 2, 3. So this vertex appears on BFS layer 0, 1, 2, 3. And if I have a complete decomposition into tripods, it also appears in some tripod. And in this case, it appears in the pink tripod. So in the planar 3 tree that I get here, so that's the graph H, that vertex appears in one of the tripods. And so I can think of the vertex in my graph basically as having 2 coordinates. One of them is its BFS layer, and the other one is whichever vertex of H that it contracted into. And another view of this is to imagine the following. You take whatever this graph is, H here. It's not complicated. It's a planar 3 tree, or part of a planar 3 tree anyway. And you make copies of it. And you take this path and you make copies of it. So for each vertex of H, there's a copy of this path that goes through those vertices. Okay. So you get this nice grid. And now you also, so you've got all these edges inside a layer, you've got all these vertical edges. And now anytime you have an edge inside a layer like this, you also add the corresponding edges from this layer to the next layer. So now you get a big graph. You get a big graph that looks kind of grid-like. So that thing is called H times P. You can kind of see that, and this thing here is called the strong product. So it gives you this big graph. And finally, if I tell you which layer you're in and which tripod you're in, right? So like this guy here, I might say it is in this layer and this tripod. Well, I almost know what it is. What I know is that, right, each of the legs of the tripod is going up in the BFS layers. So if I know the layer it is and it's on this leg, then it's that vertex. If I know which layer it is and it's on this leg, it's that vertex. And if I know which layer it is, this leg, it's on that vertex. So I don't quite know what it is yet. I know what it is up to 3 locations. It's on one of the 3 legs. I'm just not sure which one. So you blow up this graph a little bit more by taking each vertex in here and putting in a triangle. So just splitting it into 3 copies. So now your vertex really has 3 coordinates, which are which tripod you're in, which BFS layer you're in, and then which leg of the tripod you're in. And from that, I can tell you exactly what your vertex is. It sounds very strange and abstract, but the point is this thing here is a planar graph, a really complicated object. Like you've heard of the 4-color theorem. So the 4-color theorem had 2 proofs in the 1800s that each were believed to be correct for 11 years before they were discovered to be wrong. And then it took about another 90 years before there was a correct proof that even then needed computers. So there's still no really human readable proof of the 4-color theorem. Super simple thing about planar graphs, a simple statement to make. It's incredibly difficult to prove. So planar graphs are slippery and complicated. On the other hand, these 3 objects are simple. Path is very simple. There's a picture of it there. K3, that's just a triangle. And H is one of those planar 3 trees that I was just discussing. They're fairly simple, much simpler than these planar graphs. In particular, they have those small separators of size 3. So it turns out that breaking up your planar graph this way is a key step in solving many problems. So if you can manage to break your problem down into solving it for this, this, and this, then you can solve it for any planar graph. And these are somehow much simpler. And I'll present some of those, some applications of that next class. But for now, let's prove this theorem. All right. So if there's any mathematicians here, you may have heard of this thing called Sperner's lemma, or if you've taken a game theory course, you may have heard of it, or a topology course. So it's a lemma that pops up lots of times weirdly in like topology and somehow, let's say, continuous contexts. So where things are, continuous in some way, even though it's actually just a lemma about graphs, but it ends up being useful to prove these kinds of things. So I'll show you the baby version of this thing that we need. So it has to do with what are called near triangulations. What's a near triangulation? Well, it's a graph where every face except one is a triangle. So this is a near triangulation. If I do it correctly, every inner face here, there's another one, and another one, and another one, lots or not. Every interface here should be a triangle. So the one exception is the outer face doesn't necessarily have to be a triangle. So the outer face is the complement of a convex polygon, let's say. And the version of Sperner's lemma that we need says that if I take the vertices of the graph and color them with 3 colors, and it's a really actually simple version of it, in such a way that the outer face sees, if I walk around this outer face, I see, let's say, all the reds, then all the greens, then all the blues. So 3 intervals, an interval of red, an interval of green, an interval of blue. No sort of flip-flopping in between. And I color all the vertices, including the ones inside. Then what I'll be able to find, no matter how I finish this coloring, is a triangle in here, actually a face even in here, that has all 3 colors on it. Okay. So I'll always be able to find a face in this graph where I see all 3 colors. And I mean, this could be degenerate. And this is somehow a nice picture where it shows up in the middle, but it could be degenerate. The face could even be, nothing says you can't have a triangle like this with all 3 vertices on the outer face, or 2 of the vertices on the outer face, or 1 or whatever. And this could even be an edge of the outer face. So all of those things are allowed. Okay. So that's Sperner's lemma. And if you want an idea of how to prove this, at least this baby version, there's a nice way to do it. Just find a place, for example, where you have these 3 intervals. So find a place where you go, let's say, from green to blue. So there's an edge on the outside where one endpoint of the edge is green, the other endpoint is blue. So think of that as a corridor that you can walk through. Now, there's a triangle on the other side of that edge. What color is that vertex? If it is pink, then you're done. You found the triangle with 3 colors on it. If it's not, then you know what to do next. So let's say it's green. Then again, from here, I just want to walk through an edge that has 2 different colors, and there's only one of those edges, so it's obvious what I should do next. And now look again and see what color is this thing. If it is pink, then you are done, and if it's not, you know what to do. So, I don't know, let's say that it's green again. So I don't want to walk through the green edge. Instead, I'll walk through this one. Well, now I know this color is already colored, so I should walk out this one until I get to one that is pink, or, well, you might say until I make a cycle, but I can't make a cycle because I can't walk through an edge. If I made a cycle, that means I entered the same triangle twice. But if I've seen the triangle, it's because there's only 2 colors on it. In fact, I've entered it 3 times. The first time, and then I left it, and then I came back to it, which means I've actually gone to it through all 3 of its edges, but I never walk across an edge that has 2 vertices the same color, right? So let me just, right. So if I enter it, it's because it is green and blue. And then I leave it through one of these 2 edges, depending on the color of the 3rd vertex. And now if I'm going to come back to it, so look at the first triangle I ever come back to. If this is the first triangle I ever come back to, then the only way I could get back to it is through here. But if you look at my rules for walking, I never walk through an edge that has both endpoints the same color. So this thing doesn't cycle. If it doesn't cycle, how does it end? Well, it ends because it walks through a blue-green edge, and the 3rd vertex on that triangle is pink. Okay. So that's Sperner's lemma. All right. Let's see how we can use that. So remember, we had our BFS tree. We put on this special vertex just to make things a little bit cleaner. And what we want is one of these tripod decompositions. So, well, let's take as our first tripod. So remember, the BFS tree has that in it. So in particular, trees have no cycles. So this edge is not in the BFS tree because that would make a cycle. This edge is not, and neither is this edge. So that means here's a three vertices that have well, the 3 vertices, they make a 3 cycle, and there is no none of the edges of that 3 cycle are in my BFS tree. So this qualifies as something I can make a tripod out of. So we make that. No, actually, even easier. Let's be a little bit simpler. All right. Let's take let's take this to be our first tripod. Okay. So just this, and this, that's a triangular face. So it looks like that. And we take that, and that. Oh, no, I'm sorry. Go back to what I said first. Our first tripod will be this vertex by itself, this vertex by itself, and maybe this this edge, right? So that is a very simple path in my BFS tree. It's just a vertex. So is that, and then this is a path going up in my BFS tree. Okay. So all right. So now I've got somehow this tripod. And I'll pretend for a minute, even though these things are all in the same tripod, I'll pretend for a minute that they have different colors. It's not actually necessary, but let's pretend that they have different colors. Okay, so I've got one thing built so far in my decomposition, the green tripod. So let's call this colors 1, 2, and 3. Now, if I look at any vertex other than these 4 that you see in this picture, so they're all going to be inside this triangle, each one of them is part of the BFS tree. So in particular, it can follow a path from itself in the BFS tree up to the root. Okay. Now, this vertex is inside this triangle. The root is outside this triangle. So in order for this path from this vertex to get to the root, it has to pass through one of these 3 things. Okay. So I look at that path. Maybe it's this one. And I say, this passes through the vertex that I called 1. So I will say the color of this vertex is 1. And I take some other vertex and look at its path. Oh, maybe it also goes through 1. So the color of this vertex is called 1. And some other one, I don't know, maybe this one. This one goes up to 3. So it gets color 3. This one maybe also goes up to 3. Gets color 3. And you know, this one maybe goes off to 2. Gets color 2. So everybody inside here gets a color. 1, 2, or 3. And if I think about what's inside this triangle, so I've colored everything, and on the outside the colors are 1, 2, and 3. So all 3 colors, each color occupying a consecutive interval. So by Spooner's lemma, there's going to be a triangle that has all 3 colors on it. So a triangular face that has all 3 of those colors, which means that this vertex, if I follow it up to the root of the BFS tree, leads me back to 1. This one leads me to 2, and this one leads me to 3. Okay. All right. So my tripod, the next tripod in my decomposition will be, it'll have these 3 vertices plus the path all the way back to 1, but stopping short. Plus the path all the way back to 2, plus the path all the way back up to 3. Okay. So I don't know, let's make that the pink tripod. It's defined by the pink triangle. And well, so far, if I look at what would happen if I was only thinking about this graph, well, I've got a sort of three things. I got this thing is all by itself. I got the green tripod, and I've got the pink tripod. So now we forget about everything that we colored here, and we focus on what we're going to do next. Okay, so this is a triangular face. There's nothing inside of there. We don't have to worry about that. But there's still stuff in here. Okay. And there's still stuff in here. So let's call this A, this region A, this one B, and this one C. And if I think about what's happening here, that's telling me that whatever graph I was looking at out here, so this big thing, this tripod splits it up into three graphs. And there can be no edges from A to C, no edges from B to C, and no edges from A to B, because the graph is planar, and we already have these paths that, to get from A to B, I would have to cross some edge that I know is in my graph. So somehow this splits it up into three subproblems that I can attack individually. Now, if I look at one of those subproblems, well, let's say the subproblem A, what do I see? Well, A is bounded by two things: the pink tripod and the green tripod. So that's only two things, but just to make my life simple, or to get out of this sort of boring cases at the beginning, I'll just say, let's take the first vertex of this thing and just pretend for a minute that it's a different color. Let's call it blue, just so that I have three colors here. So now I have a green interval, a blue interval, and then a pink interval. And if I look at a vertex in here, it has a path in the BFS tree up to the root. It's stuck inside this cycle, so that path has to cross this cycle somewhere. And that means it has to cross one of these, pass through one of these vertices. And, if the vertex passes through, if the path to the root passes through the blue vertex, then I'll call this thing blue. If it passes through one of the green vertices, then I'll call this thing green. Same with this one. And if it passes through the pink, which it could do, then I will call this thing pink. And what is Sperner's lemma going to tell me? It's going to tell me that I can find in there a triangle that has three different colors on it. So maybe this is the triangle. Okay. And now I take the tripod, which is this piece, and this piece. Let's call that the white tripod, and it's being used to break up A. And it actually breaks up A into three parts: A1, A2, and A3. And I can recursively do the same thing on each of these parts. So Now, if we back up a little bit, here's where things get a little bit interesting. Once I've done this, if I look at part A1, I'm finally into the full case. So A1 has on its boundary the white tripod, some of the pink tripod, and some of the green tripod. And it's green, pink, and white. 3 intervals, exactly what Sperner's lemma is set up for. So in there, I'll be able to find a triangle. One vertex leads back to a green boundary thing, one leads back to a pink boundary thing, and one leads back to a white boundary thing. So the generic picture at any step is I have a part of my graph, some part of my graph which I'm working on. So that's a face like this, that is showing up in, so it's the face of the graph that I've made with all the tripods so far. There's still vertices in here, and so I still need to decompose this. But on the boundary of that face, there's exactly 3 tripods that contribute to it, 3 or less. And if it's less, then it's just easier to manage. And so then I go and find my Sperner triangle, which leads me back to these locations and leaves me with 3 subproblems, this one, and this one. And the key point is that if I look at this subproblem here, it doesn't have any pink on its boundary. So over here, there's no pink on the boundary because the pink is separated by the path from the green to the blue. If I look at this subproblem here, it doesn't have any green on its boundary because the green gets separated from this thing by the white tripod. And if I look here, it doesn't have any blue on its boundary. So if you give me one of these subproblems with 3 colors on its boundary, Sperner's lemma lets me find a triangle. The tripod that I build from that triangle gives me 3 subproblems, each of which only has 2 colors on its boundary. Pink and green plus white. Pink and blue plus white. Blue and green plus white. So I will only ever have these subproblems with 3 colors on the boundary, which is what Sperner's lemma lets me tackle. Now, all right, so that's how you build this this so-called tripod decomposition. So why is this thing a planar 3 tree? So why, when I contract this, would I get a planar 3 tree? Well, you can almost see it, what's happening from this picture, right? So at every step, at every step, I have this thing, a collection of tripods, that if I were to contract them, then I would get a planar 3 tree, and with a bunch of these triangular faces. And at the next step, right? So in my contracted graph, if I were to contract before I looked at this white thing, I would find a triangular face that looks like this: pink, blue, and green. And now I build this in, so inside this uncontracted graph, I find the tripod that I want. And that thing, when I contract it, that's going to become a vertex, which is adjacent to the pink, adjacent to the green, and adjacent to the blue. And more importantly, it's not adjacent to anything outside of that. Right? This white tripod is not going to be adjacent to anything outside of this picture because, well, it has no, there's no, certainly no edges jumping over these paths here. Okay. So that is, that's the proof of this thing, which has a name. So this thing is called the planar product structure theorem. And if you ever read about it, it's stated this way: every planar graph G is a subgraph of H times P times K3, where H is a planar 3 tree, P is a path, and K3 is a triangle, a cycle on the graph with 3 vertices that makes a cycle. And that's just by carefully reading the definition of this product and just going through the definitions of all these things. So the K3 is coming from the fact that a tripod has 3 legs. In particular, it can have 3 vertices from any level of the BFS tree, which is represented by the path P. And then H, well, that's just the graph that you get when you contract these things. And I'll just very, very quickly show you how you get a planar separator theorem from this, basically immediately. Okay, so this theorem here says that if you give me any graph G, any planar graph G, I can find it, it's contained inside this picture here. Okay. So that's the picture of H times P times K3. So it's a subgraph of there. This has way more vertices than my planar graph, but somewhere in there, the graph is hiding inside there. So what I can do is walk down the path until I get somewhere where there's less than or equal to n over 2 vertices of my graph up here, and less than or equal to n over 2 vertices of my graph down here. Good. Now I walk back up to the first place where one of these layers has, let's say here, less than or equal to the square root of n vertices. Okay, so on here is less than or equal to, so in this layer, if I look at where my graph is hiding in there, less than square root n vertices are hiding on this layer. And I do the same thing, so, but on every other layer, there's more than square root n vertices. And I do the same thing in the other direction finally I get to one which is less than or equal to square root n vertices. Okay. So here's these two layers. And together, they have at most 2 root n vertices. And they break my graph up into 3 parts. Up here is less than n over 2. Down here is less than n over 2. That's just because already up above here was less than n over 2, and down here was less than n over 2. In the middle here, who knows? Could be a lot of vertices. Could be, in fact, all of them. So now, the other thing that I know is, well, every level in between here has more than square root n vertices. So the number of levels in here is less than or equal to root n. So the number of layers between this top part and this bottom part is less than or equal to root n. Well, now I take my graph H, and I imagine that the vertices have weights on them. And I go in H and I find this 3 vertex separator, which splits those weights into equal parts. Right? So that means that I find a like 3 things here, which if I remove them, they break this graph between here and here into roughly equal parts. And I take those from each level. Okay. So this part up here is less than n over 2. This part down here is less than n over 2. And in between here and here could have been big, but this breaks it up into 2 parts that are each of size less than 2n over 3. How big is the separator? Well, this piece has size less than root n. This piece has size less than root n. This piece has 9 vertices per layer, and there's only root n layers. So that's not more than 11 root n vertices total in the separator. Okay. All right. So that is a good place to stop for today. And next class, we'll look at a few applications of this stuff.
Sorry, Pat, when can we expect the grades for assignment 2?
Real soon now. Yeah, hopefully in the next week or 2.
Okay, thank you.